That seems to be the way it works. A load of mathematicians come up with a theory, and everybody says, I don't believe a word of that, that's the craziest thing I've ever heard. There's an interval of about 20 years, and somebody makes a measurement, and half the time, even when they make the measurement, they forget about the poor guy who made the prediction. Galileo here, for example, never got the Nobel Prize, because by the time they measured the thing, they'd forgotten all about it. And he got very, very excited about this, wrote a lot of letters. And afterwards they had to admit, oh yeah, well actually we just forgot. We didn't overlook you, we just didn't know you existed, you know. But he got a prize for it afterwards. That happened again down here. By the time the Kobe group went around and they got a Nobel, but by the time they made their measurements, everybody had forgotten about the theoreticians who predicted. So that's the tough lot of mathematicians sometimes, that they make predictions that are so far ahead of time that by the time somebody measures it, they've forgotten about what prediction was. Okay, so what about some questions? Anybody have any questions? If any of you have any questions about the nature of space and time, I'll do my best. It's not something any of us really understand. Sorry, yeah, just raise it.
The way we're talking about the way time has changed according to where you are from the source of gravity.
Yeah.
And does that mean that time will be slower?
Which way does it work? Yeah, there's an effect called, well, the way to see it is an effect called time dilation. And what it means is the stronger the gravitational field, the more it stretches the time. So you and I are actually living in stretched time, what's known as proper time out in space. Our hour is longer than their hour. Yes, there is a very, very slight difference. That's one of the things about modern science, that we can now measure these things. It makes no difference to you in an everyday way, but you can actually measure it. It's even different on the top of the mountain than it is down here. It's kind of weird, you know, but it's only different by 0.0000001%, but it can actually be measured. The other interesting thing, I'm glad you asked that, and I didn't get time to mention it, but the other interesting thing that some of you may have heard of is time is also affected by motion. It's not just affected by gravity. If you move fast enough, time also changes. And that's that famous thing you always hear about, the twin paradox. But it is true that if somebody is moving fast enough, a clock they're carrying, for example, on their belt or whatever, will measure differently from the clock than if they're stationary. And that's, again, a very, very strange idea. But it's because we now know that time and space are not as completely separate as we like to think they are. They just look that way in the normal circumstances. But for example, for things coming close to the speed of light, what their experience of the time is quite different. If I can give you one example for all of you, it's something every student should know, is every particle has a lifetime. Just the way you and I have a lifetime, our average lifetime is about 70 years. So you might live 65 years or 75 or whatever, but you're not going to live 200 years. Yeah, well, there's an average. Every particle, as in the things that are inside the atom, has a certain lifetime. But nowadays they can put them in an accelerator, and they accelerate them up to unbelievable speeds, almost as fast as light. And they find the lifetime of those particles is completely different. They live for 20 times longer than they should live. And when they first discovered that, yet again, somebody discovered this by accident. What the hell does that mean? But that Einstein had predicted that years ago, but nobody thought to go look at it. It actually happens. Yeah, that's exactly what happens in those hadron accelerators. One of the advantages of having the particles at that high energy is they're moving extremely quickly. Because they're moving extremely quickly, they live much longer than they would normally live. They normally don't live long enough to see them at all, but they live for days because they're accelerated so fast. That's exactly right. The new experiments will start up in 6 months' time, so hopefully we'll see some interesting results. He's talking there about there's a very big accelerator in Switzerland where they measure these things, these kind of effects in the world of the subatomic, because the world of the subatomic is very, very, very close to the world of cosmology. And it's a big European project which will start in about 6 months, and we expect to see some very, very interesting things. So what about, what is the answer to the question, usually somebody asks, well, what was there before the Big Bang? Anyone like to attempt to answer that? What was there before the Big Bang? Well, you'll often see this in magazines and books and blah, blah, blah. The sort of technical answer is actually very simple. The technical answer is because we think time is part of our universe, there is no before. It's exactly like saying what is north of the North Pole. I mean, if time is part of the universe, by definition the universe began with the Big Bang. So there is no before. If you like, our time begins with the Big Bang. I forgot to mention that another sort of trendy idea now is there may be parallel universes. And what we mean by that is there may be other universes that we know nothing about and never will know anything about, because by definition they were brought about in a different Big Bang, and that's quite possible. But that doesn't affect us. Our time begins with our Big Bang. Yes. It's one possible. It's the most fashionable alternative, let's say, or the biggest alternative to inflation. What membrane theory is, and this comes from the world of the subatomic. Some of the models they have for how subatomic physics works. If you apply them to the beginning of the universe, you come up with the idea that maybe the Big Bang was a repetitive process. Yeah. The only thing about that is, the reason I don't mention it much is, so far we've no evidence whatsoever to support it. It's just a theory, but it is a nice idea. Well, I think we can leave it at that. Can you just speak a little louder? Can everyone keep quiet so we can hear? Oh, yes, that's the other big question. It's a very good question. People always say, in the end, it's like conservation of energy. How can something come from nothing? There's two sort of standard answers to that question. The first of all is, what we call something now, believe it or not, can actually add up to zero. Because it sounds strange, but one of Einstein's discoveries, which we now think is right, is that mass, that funny thing that causes gravity, is actually just a form of energy. And that's the big answer to gravity, by the way. Mass is a form of gravity. Now, the mass is a form of energy. Now, it's possible that when you add up all the mass of the universe and you add up all the energy, you actually get zero. You wouldn't think that. But the form that mass is in is the opposite form to moving energy. So when you add the sum total, you may actually get zero. So from a strictly mathematical point of view, it's actually perfectly okay to have zero, a Big Bang, and the present universe. Because the sum of the energy, even though you and I feel that we're full of energy, the sum of the energy universe may very well be zero. That's the sort of first standard answer. There's another standard answer, which is, in terms of the way in which it happens, which is also interesting. How does, something, okay, even if that's true, how does that nothing become something as a physical mechanism? The answer is, one of the funny things about quantum physics is because we can never be absolutely clear on measurement. Like in quantum, you never have something is 1 meter. It's always 1 plus or minus. There's always a certain uncertainty. The even zero, even nothing, is not actually tight in quantum physics. Nothing is always nothing plus or minus a small amount. So what happens is particles and what we call antiparticles can appear out of the vacuum for a very short time and disappear. And that doesn't, that's perfectly okay. It doesn't violate conservation of energy. But with inflation, if a particle suddenly appears, just in a fraction of an instant before it disappears, if inflation gets hold of it and blows it up, that could become a Big Bang. And that is actually what they think. So the standard quote is, in the beginning, there was nothing at all, and then suddenly there was a free lunch. And the idea is that literally it would only take one particle to appear for a fraction of a second. And according to quantum, that could happen. If inflation got hold of that particle, it could literally blow that up into the whole universe in that time. So our entire universe could actually be a free lunch. But I stress, these are sort of the thinking in maths at the time. There's absolutely shag all evidence for that. We don't know. We just think that. So I think you all look like you need your lunch.